Oh yeah, sometimes.
I just switch the microphone on, and then I talk, and then it's all good. And I just stand there as, as a yes. Thank you.
Have you tried that?
You can, Nina, sorry, you can keep it on and off as you wish. It's muted until the seminar starts.
But then it's maybe easiest if I keep it on.
Exactly. So you
Because
don't.
then you will forget otherwise.
Yeah, exactly. So you can just.
Not so much.
There's more seats in the first row, Marlene.
First, so first. And then also.
And welcome. I'm using the microphone, not for those who are following the stream. And welcome. I'm using the microphone, which is meant to facilitate the. Seminar, and the usual procedure is that today it's actually the usual procedure is research area. And the usual procedure is research area. And the usual procedure is research
because we both, Thorsten Mauritsen, who will give the second presentation, and I myself, Torben König, we both started rather new as Research Area 1 leaders. So we thought it's a good opportunity to give an overview on what we are doing and give you the possibility to get to know us. So I will start with the first presentation, and I'm a global climate modeler and working at the Swedish Meteorological and Hydrological. I will start with the first presentation, and I'm a global climate modeler and working at the Swedish Meteorological and Hydrological. I will start with the first presentation, and I'm a global climate modeler and working at the Swedish Meteorological and Hydrological. I will start with the first presentation. I'm a global climate modeler working at the Swedish Meteorological and Hydrological. I will start with the first presentation. I'm a global climate modeler working at the Swedish Meteorological and Hydrological. I will start with the first presentation. I'm a global climate modeler working at the Swedish Meteorological and Hydrological. I will start with the first presentation. How changes in the Arctic, ongoing changes, might affect lower latitudes. So there's an ongoing discussion that especially cold winters and cold periods in winters could be due to changes and loss of sea ice, especially in this area, Barents Sea area. Then we will return to the Arctic and see what happens with the fresh water that flows out of the Arctic. So the Arctic is a region which is very fresh because there are a lot of rivers going in, and precipitation is higher than the evaporation. So fresh water is exported out of the Arctic into the North Atlantic especially, and can there affect the large-scale oceanic circulation, which then in turn can also affect the Gulf Stream back towards Europe. Okay, let's have first a view on the observed ocean heat transport into the Barents Sea, and we have the Barents Sea here on the left side. This is the Barents Sea, this is Norway, Svalbard, and there is a section where a lot of observations have been done. And I show here the transports of heat across this section. And if we look only at the two thick lines here, I think it's a red line shows the ocean heat transport, and the blue line shows the sea ice area in the Barents Sea, but it's inverted. So high values mean less ice, and low values mean more ice. So these are anomalies. And what you can see is that there is some relation maybe between these two, and for this short period between 1998 and 2010, both seem to show some kind of trend or long-term variability. If we look at somewhat longer time periods, we don't have the ocean heat transport itself, but we have the temperature in this section here. And that's what we can see here. It's the temperature, this line, and again, the sea ice. Now we have a longer time period of around 30 years. And here, even here, we see now the better, a close relationship between the temperature and especially between the trends in the temperature and the trends in the sea ice. So there seems to be some relation between this ocean heat transport and sea ice in the Barents Sea. Now we move into the modeling world, and this allows us to look at longer time periods and more data. And we use the global coupled model EC Earth here. And these are results from a 350-year-long so-called control simulation with this EC Earth version 3.01, which used constant year 2000 forcing. That means forcing, external forcing from year 2000 are repeated every year again for the 350 years. And what you see is the correlation between the ocean heat transport and the 2-meter air temperature for timescales of a decade. So we have 11-year running means we are using. And the same for the ice concentration. So what we see for the ocean heat transport across 70 degrees north, I would say. So what we see is that we get high correlations in the North Atlantic itself, but also in large areas of mid and high northern latitudes. So if we have increased ocean heat transport to the north, we get a warming in most of mid and high northern latitudes. And at the same time, we have a negative correlation with the sea ice concentration, especially in the North Atlantic sector of the Arctic. So we get less sea ice. So what happens in the relation with the sea ice concentration?
Again for this years, but from the CMIP-5 simulations, CMIP stands for Coupled Model Intercomparison Project, 5th phase.
So what happens in the relation with the sea ice concentration?
Again for this years, but from the CMIP-5 simulations, CMIP stands for Coupled Model Intercomparison Project, 5th phase.
So what happens in the relation with the sea ice concentration?
From the CMIP-5 simulations, CMIP stands for Coupled Model Intercomparison Project, 5th phase.
So what happens in the relation with the sea ice concentration?
From the CMIP-5 simulations, CMIP stands for Coupled Model Intercomparison Project, it's the case here.
So what happens in the relation with the sea ice concentration?
From the simulation, the comparison project, it's the case here.
We can see is that the total heat transport in the ocean into the Arctic is strongly increasing in the 21st century. It starts already to increase at the end of the 20th century, and then even more increasing. And we also see that most of this increase is due to an increase in the ocean heat transport through the Barents Sea opening. So that's the area where we see the largest increase of heat transport into the ocean, into the Arctic, in the ocean. So this shows now the spatial changes in the Arctic until the end of the century in RCT 4.5, so in the lower emission scenario. And it's clear here from the figures that the Barents Sea is a hot spot area, the key area of climate change in the Arctic. Especially or specifically there where we get the increase in the heat transport, we get a strong decrease in the sea ice concentration. And here in the Barents Sea, we lose all sea ice even during winter around 2030 to 2040 in our model simulations here. We also get stronger reductions here in the Beaufort Sea, but mainly in summer. In winter, it's still ice covered. So the values, these are annual mean values. Therefore, these annual mean values reduction is not as large as in the Barents Sea. Then the reduction of sea ice leads to a strong increase in the ocean heat release to the atmosphere, both in the sensible and the latent heat flux. And as a consequence, we see a strong warming in this area. The entire Arctic shows an amplification compared to lower latitude temperature amplification, but in the Barents Sea area, we get a warming of annual mean temperature of 10 to 15 degrees. So many studies now linked this sea ice variation and especially loss, especially in the Barents Sea and Kara Sea region, to temperature in lower latitudes, especially to winter temperatures in Eurasia, over Eurasia. And you might have seen that kind of articles in the last decades. Almost all winter-like condition in Europe further to the south is linked to Arctic sea ice melt or Arctic amplification warming. The background for this is this pattern here on the top right, which shows the wintertime surface temperature trends between 1990 and 2013. We see a strong warming over the Arctic, but at the same time, we see a strong cooling, especially here over Eurasia. And at the same time, the sea ice was strongly reduced. So many studies were trying if this, or testing if this might affect this. And many came to the conclusion that it has at least a rather strong impact on this warming and cooling pattern for this time period at least. So we also participated in these studies, and here you see the correlation between November sea ice in the Barents Sea, Kara Sea, so in this area, and the following winter sea level pressure. And what we see is that if we have more ice, we get reduced pressure over the Arctic and the Nordic seas and increased pressure further to the south. That gives us stronger west winds transporting warm air towards parts of Europe and Asia. And so if we have a reduction of sea ice, a loss, this would give us a cooling. And it's rather the same area as found here by Cohen et al. However, the time period is rather short. It's only 30 years, so on climate scales, this is rather short. So we were interested if this is a robust signal or if it's just by chance, because there were also many other things changing at the same time, not only the sea ice in the warming world. So we now used another data set, which just goes a bit longer back in time. And for the period 1980 to 2013, we get the same correlation pattern as before. But if we go further back to 1960, the signal is almost disappearing. So it's very weak by just adding another 20 years. So it seems from these results that the signal is not so robust. However, it could be that it's just due to the fact that sea ice data before 1918 are rather uncertain because we don't have satellite data. So to further explore this connection, we performed a number of coordinated multi-model ensemble experiments with international partners together in the project, which was called Green Ice. In total, we used 6 global atmosphere models, and we performed simulations from 1982 to 2014. And we forced our atmosphere model with, in the first experiment, with daily observed varying sea surface temperature and sea ice concentrations at the boundaries, which are then given to our atmosphere model. And we are not doing only one simulation per model, but we are doing between 10 and 30, in average 20 ensemble members. And these 20 simulations per model, they differ only in a small perturbation in the starting conditions. Otherwise, they're exactly the same. In the second experiment now, we replace these sea surface temperature variations with climatological sea surface temperature from 1982 to 2014. So we don't have any trend and we don't have any interannual variability. So the second experiment should give us just the effect of the sea ice. That's what we get if we look at the winter temperature trends. On the left side, we have the era interim data, so observational based data, which show a strong warming, especially here in the Barents Sea, Cover Sea, but also in the Labrador Sea and the Baffin Bay. And it's a bit hard to see because it's hardly significant at the 95% level, but there is a rather strong cooling over Siberia, which is about 1 Kelvin per 10 years. You might see it here at this spot, which is significant. But if we look at our experiment, we see we produce the warming over the Arctic, but there's no cooling at all over Siberia. Then if we only look at experiment 2, where we only varied the sea ice, again, sea ice over the Arctic, the warming is reproduced. Also over Scandinavia, the sea ice alone seems to lead to some warming, but not no strong signal here over Siberia. So conclusions from that would be that this warming, this cooling over Siberia might just be due to natural variability. But of course, you could argue that the models are not able to reproduce the processes that link the sea ice changes to the Siberian temperature. So to check that a bit, we focus now here only on the Eurasian area. Again, on the top, we have trends in temperature and sea level pressure. And here you also see that sea level pressure shows a strong positive trend at the Siberian coast, which attracts then cold air into this region, leading to the cold trends here. So, but in the models, we now focused only on the 5 coldest ensemble members from the 120 total simulations which we have. And with coldest, we mean here the 5 members showing the strongest negative, or the strongest negative trend in this box. And if we focus only on these 5 coldest members, we see that we get similar cold values, cold negative trends as in the observations, maybe even a bit stronger. And we get also a similar atmospheric circulation response, which then again here transports the cold air into this Siberian box. So the models are obviously able to reproduce such cold trends, but most of the ensemble members are just not doing it. They're showing positive trends, warming trends, which might strengthen the assumption that this could also be due to natural variability. Okay, then further, most studies analyzing this, they end 2013 or 2012. So we were interested what happens if we continue the time series towards the last winters. So here you see on the right side in the time series what happened until 2013. This is the sea ice, different months and seasons. It's reduced in the Barents Sea, Cover Sea, strongly reduced. The sea level pressure anomaly at the Eurasian Arctic coast, which is important for the temperature, shows a positive trend at the same time. Temperature anomalies are going down. But already here we see that especially the last 4 years of this period, which were very cold, and these are shown here, only the anomalies in these 4 years, so very strong cold anomalies and a very strong positive sea level pressure anomaly here. You also see that we have a negative trend in the Pacific decadal oscillation and in the North Atlantic oscillation. So the main atmospheric circulation patterns in the North Atlantic and Pacific regions. But if we now update, then we get this. So the sea ice stays low, but the sea level pressure anomaly goes down again. The temperature goes up again, so it's getting warmer than normal in the last 4 years. And also the PDO and the NAO shows that exactly in this year a jump upwards. So I will not go too much into detail, but just by the fact that the sea ice is still low and temperature goes up, it shows us that the sea ice is not the only one dominating factor of the temperature. We did some more analysis showing that the sea ice has some effect, but this is overcompensated by changing NAO and PDO, which then gives us this warming back over Siberia. Okay, in the last part, I will talk a bit about the Arctic freshwater and ocean circulation. So why is freshwater in the Arctic of importance? If we look here at the Arctic basin, we have a lot of rivers coming into it. and we have snowfall and more precipitation than evaporation, and then it gives us a fresh surface and ice, which then also might melt. And since we get more fresh water in, we have somehow get rid of it, so the fresh water is exported to keep the balance, the budget. And rather near to the ice edge, we have the areas which are very important for the ocean circulation. That's here in the Greenland Sea and in the Labrador Sea. And in these areas, water is getting cold by loss of heat, sinks down, and so-called deep oceanic convection. And then the water moves to the south and comes back as warm, salty current, where the Gulf Stream and the North Atlantic current is part of it. So, and this circulation is also called Atlantic Meridional Overturning Circulation, AMOC. So if we now increase the fresh water that comes into these regions, that might make the water, or would make the water less dense, and because fresh water is less dense than salty water, and this could lead to a reduced convection because the water is has a too low density to sink down, even if it's getting cooled. So we're interested in what happens in these freshwater exports. So first we see in the 21st century, so again, Easy Earth simulations, future simulation scenarios, that we have an increase in both the river runoff into the Arctic and also an increase in P-E in this Arctic area. And this shows that there's more freshwater coming into the Arctic. So either the freshwater is stored into the Arctic, in the Arctic itself, or it leaves the Arctic through the straits. So, and here on the top, we see the content of freshwater, which is in the Arctic. And we see it's strongly increasing. It's increasing until year 2060 or so. Again, we have two different scenarios here. But thereafter, it stays rather constant. So what we would expect is that we see an increase in the export of freshwater out of the Arctic from the middle of the century. And that's also what we see if we look then at the freshwater exports here through all these sections. The black line gives us a total freshwater export out of the Arctic. Negative means out of the Arctic. And we see, as expected, that in the end, we see some increase in the export out of the Arctic. And this is mainly due to an increase in the export through the Canadian archipelago, while the export through Farm Strait is somewhat reduced, mainly due to the fact that we have less sea ice. Okay, how can this then affect, or is this then affecting this convection? To analyze this a bit more in detail, we defined and used a convection index, which we called DMV, deep mixed volume. And I will not go into detail how we calculate that, but if it's high, it means we have a lot of deep water formation in convection here. If it's low, it means the water is not going, so not so much water is convected down. And then we also see the strength of the Atlantic Meridional Overturning Circulation at 26 degrees north and 48 degrees north. And what you see is that in the Labrador Sea, there is a clear linkage and for decadal values of this index, convection index, and the AMOC. And the convection is leading the AMOC with a few years. And then we have a decay of the convection, and also the AMOC is substantially reduced. However, we see that the strong reduction in the convection already occurs before the freshwater was strongly increasing. So most of this decrease, which we see here, is not due to freshwater exports, but is due to warming of the ocean surface. But then later on, also the freshwater is contributing. So some conclusions. Ocean heat transport into the Arctic is likely to increase, and it seems to be important for the entire Arctic and its change. And particularly for the Barents Sea, it's important, which is also popping up as a hotspot region for Arctic climate change. And the sea ice loss in the Barents Sea was linked to mid-latitude cooling trends, and there was strong correlation, statistical linkage between 1980 and 2013. But the linkage might be at least partly due to natural variability. And we also found that Siberian temperatures were returning to normal values after the winters 2013, 2014. So the cold period in the years before
stopped. Arctic freshwater exports, they are increasing in the second part of the 21st century, but we also see a lot of increase in the freshwater content in the Arctic itself. It has some impact on the North Atlantic deep convection, but most of the reduction in the convection is due to warming. And the reduction in the convection is also reducing our the Atlantic meridional overturning circulation. So, and this is, of course, true for our easy Earth model, and most of these results and could be different in other models. Then after that, I would just to show one short slide, which is from the newest CMIP-6 simulations from easy Earth. We have performed now a number of historical simulations. 3 are shown here, and then different scenarios to the future, 5 different scenarios, 3 members each, and this is the global mean temperature. And what you can see, one thing is strong variation in the historical period particularly, and then a rather strong increase between a bit more than 2 Kelvin in the lowest emission scenarios and up to a bit more than 6 Kelvin in the highest emission scenario. Thanks a lot for your attention.
You need to have the mic, otherwise you can't hear it. Questions to
Yeah, thanks for the great talk. I think you mostly show this recent past or present days. And we use this easy Earth model for the past warm climate, and we also see this very strong Arctic warming. When we compare with other models, it seems that the easy Earth show much stronger than others. I don't know if you also find a similar character when you compare with other models for the present day. Is this easy Earth overestimate this warming, or it's true?
For the CMIP-5 simulations, easy Earth is in the upper half, or maybe even the upper third, but there were also models showing even higher warming in the Arctic. But it's a bit over the mean. And the main reason for that is, or might be, that we start with a bit too much sea ice in the historical period and lose quite a lot of ice. While often those models who are showing less warming in the Arctic have already from the beginning very low sea ice areas so that they can lose not so much ice. And therefore the warming is in a way more limited, as if you have a lot of ice which you can melt away. And if you in winter time take away the ice and have open ocean instead of ice, you get a warming of almost 30 degrees. While if you don't have ice, the warming is much smaller.
I followed that discussion on that basically the Arctic warming should be responsible for cooling or cold winters. For me, it was always a bit surprising. I mean, we had cold winters already before. So was there some kind of study or result which said that the cold winters which we have now are different from the mechanisms than which caused cold winters in the past?
No, I think the mechanism is relatively similar. So it's always, cold winters are always linked to the atmospheric circulation anomalies, and even couldn't see that I looked at longer time periods back and station data for Siberia. Even the cold winters in that period had a similar atmospheric circulation anomaly. And the winter 2009-2010 was the second coldest in the period since 1900, but the others were not really outstanding. What is in a way outstanding is that never before 4 winters in a row were so cold. So if you would take the 4-year average or 4-winter average, this would have been the coldest period in the 19th century and the 20th century.
Okay, thanks.
Hi, Torben. Nice talk. So you showed a strong increase of the heat transport through the Barents in the scenario runs at the beginning. And so do you get a sense for why that happens? Is it a change in circulation? It's just the temperature changes?
Yes, we looked into that and we divided into a volume part and the temperature change part. And it's mainly the temperature. About 3/4 of the increase is due to the temperature and 1/4 due to increased volume transport. And the increased volume transport is linked to atmospheric circulation changes, which leads to stronger southwesterly winds in that area. But that is something, especially the volume transport, something which can differ quite a lot from model to model.
Yeah, you said the volume transport, and I'm just wondering, how do you compute the heat transport in order to eliminate volume changes? Because it's a rather
we looked
way to do it. Normally, you'd need to zero the volume transport in order to have a heat transport that means anything.
Yeah, we divided it into a part where only the temperature, where we have the mean volume transport multiplied with the temperature anomalies and the other way around, and then the product. Of course, if you use monthly mean values, this is certainly not entirely accurate. Not convinced.
Okay. Last question.
One more question on this freshwater forcing. I guess you didn't account this melting of the Greenland ice sheet.
No,
ice sheet is fixed.
It's not. Yes, it's not included.
So this is only the sea ice melting, right?
No, the sea ice melting is not much contributing to the freshwater. It's mainly the increased river runoff into the Arctic and increased precipitation in future, which leads to increase in the freshwater in the Arctic.
That means if we take into account the ice sheet melting, then this forcing will be much larger, and then the consequences.
Yeah, but the increase in the input into the Arctic are much larger as the melting of Greenland at the moment, at least. So you would need to assume quite a large melting, but on the other hand, it could of course more directly flow to the convection areas.
Okay.
Okay, I think we have to move to the next talk. We have around 30 minutes left.
Oh, perfect. Now it works. Yeah. So I'm Torsten Mauritsen. I started working at MISO last year. I came from the Max Planck Institute in Hamburg. What I wanted to talk to you about today is what I'm doing at the moment. So I'm participating in 2 large assessments of what's called the equilibrium climate sensitivity. One is started first. It was a grassroots development in the WCRP where a bunch of people decided to work together and figure out what it is. And then the second is the next IPCC report, so the so-called AR6 or 6 assessment report. And so these are all the people that I've been working with. The blue guys here are from the AR6. Some of us are also in the other one. And then the purple group here is the WCRP people. So the forcing and feedback paradigm is really fundamental to everything in climate sciences. The idea that if you apply a radiative forcing to the Earth, for example, by changing the CO2, the temperature responds, and you have feedback mechanisms that act to restore the energy balance of the system. It's how we interpret past climate changes, and it's how we understand future projections. And so the most basic measure of this sensitivity is usually defined as the equilibrium climate sensitivity, which is the temperature response after a long time if you double CO2 over pre-industrial levels. So that's kind of a key metric. So here I'm showing results from an atmospheric model coupled to a mixed layer ocean. So it's not a deep ocean, so it doesn't take very long to equilibrate. And what we do here is we apply a doubling of the CO2 in the atmosphere. We get a strong imbalance, so more heat is flowing in than out. And then on average, after the first year, it has warmed by 1 degree and has still some remaining imbalance. And then the second year, it's warmer, less imbalance, and so on. And so after a while, it has warmed, in this case, by 3 degrees. Things are almost linear. The imbalance equals the forcing, which we can read off the y-axis, and the feedback parameter is negative. This is the slope, okay? And so you can estimate the equilibrium climate sensitivity based on the feedback parameter and the forcing you get from a doubling of CO2. And then you get a hyperbola like this. So the smaller the feedback is, it's always negative, otherwise the system is unstable. The smaller it is, the larger the sensitivity. And so these dots here are individual so-called CMIP5 models, similar to the one that Torben just talked about, which follows quite nicely this simple relationship. So why would we talk about global temperature, I guess, in this research area? It's an unusual thing to talk about. There are several reasons, but I think the main one, well, sorry, I should step back a little bit. We usually plot these temperatures like this. So this is runs from the Max Planck Institute's CMIP5 model. So these are historical runs, okay? This is a control simulation, and then 3 different scenarios into the future. And so when we presented this model, we did something funny, I think. So we took the state here, 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 and here. Okay, the maps of temperature. I'll show you in just in a moment. And all we did was divide by the global mean temperature. So every point is the warming relative to the global temperature. And we did the same for precipitation. And this is these 4 maps, okay? I challenge you to spot the difference, okay? So you could say, okay, for temperature, maybe that was easy. It's a simple thing, sort of. So precipitation, which we would maybe care more about than temperature, actually, it's the same story. You can hardly tell the difference, okay? So to first order, the global temperature is going to give us local or regional impacts if we know the relationship between the two. So let's see. I had another plot. So often you're cheated by maps and color scales and so on. So we actually did a zonal mean plot, and you can see how all these 4 states, which are wildly different, lands perfectly on top of each other, with a little bit of, oh, you can't see that. Actually, the Arctic, which is a special focus area here, has a bit more variability between them. And even for precipitation minus evaporation, same story. So then, okay, so that's one thing. So the temperature, that's good. But why climate sensitivity? And so this is from a study from the UK by Gross et al. I didn't do this, you can tell because the figures are ugly. Sorry, just kidding. No, but why would you use a divergent? I mean, this is, yeah, okay, anyway. Sorry. So what they did here was they related the future warming trends, in this case degrees per decade, in a scenario to different measures of climate sensitivity. The black ones is the one I'm talking about, equilibrium climate sensitivity. This is a popular one called transient climate response. And what you can see is the relationship between the trend into the future is much higher if you're using the equilibrium climate sensitivity than the transient, which is the yellow here. So just focus on the R² values. You're getting a much better estimate if you know the equilibrium climate sensitivity. And so how has this developed through the years? Actually, people have been thinking about this for 200 years. Fourier was maybe he sort of discovered the greenhouse effect, and you have Tyndall who analyzed absorption, and then we should be very proud. The first real estimate of climate sensitivity came from Svante Arrhenius more than 100 years ago. He was immediately attacked by people, and so there was a long period where they disagreed whether he was right or wrong, but then later it sort of picked up. There are several other estimates in this period that I didn't plot, but this one is very nice. An English guy who almost learned metrology on his own and made a very good estimate, it turns out, actually, of the climate sensitivity if you only have temperature and water vapor feedback. So it's pretty good, actually, 1.6. And then people started building models about this. So perhaps the first one was by Manabe and Weatherald, which was just a 1D model, and then later they made 3D models as well. But then it became apparent that this was a problem. So people started doing assessments. So the first one was the Charney report in 1979, and they estimated. They have. It's a beautiful report. It's 20 pages. You can read it very quickly. You can find it on the internet. It's very nice. And they have this statement: we believe, therefore, that climate sensitivity is free and between 1.5 and 4.5. That's what they said. If you go back, it's actually just based on two models. So they had one model with 2 and one with 4, and that's what they came up with, more or less. They had some pretty good physical intuition as well, I guess. So I think of this, well, you could then argue that the fact that not much has happened since in the following 40 years is a sign of lack of progress. I would say it differently. This is a hypothesis that they made in the 70s, and people have been working on proving or disproving it afterwards. And it's been a tremendously successful hypothesis, I would say. You can also notice some other things. So, for example, in the first assessment report, this was then run by IPCC, they had another model. It was supposedly better and newer, and it had a lower climate sensitivity than the ones they had before. So they lowered their best estimate, but they didn't really bother changing the bounds. And then in the second, they just kept it. They had no reason to change it. In the third, they don't give a best estimate. It's hard to agree on something if you disagree. So then in the fourth, the best estimate came back, and they raised the lower bound. And then in the fifth, they actually lowered the lower bound again and became much more explicit about what they meant. Okay. So if you look in the AR5 report, this is the basis, sort of say, that they had. They had different studies. They had these different lines with error estimates. Some didn't give error estimates. Some were different. But nevertheless, I wasn't there, so I don't know, but there was a citation by an unnamed person. The weight of ink shows us that we have to lower the lower bound again. So there was a bunch of studies that gave relatively low climate sensitivities, and so because there were many of them, they decided to lower it. I can't help showing this. This is a follow-up by Reto Knuti and co-authors from 2017. Very nice compilation. I've used it a lot, actually. But if you look at this, I mean, you get scared. How can I make sense out of all of these studies? And so we feel like this guy, okay? Yeah. We need to somehow order things, okay? So we need to change how we approach this. And so the idea has been to identify independent lines of evidence rather than just taking all these studies, because some studies are easy to make. For example, instrumental record, so historical warming studies, there's like many dozens of them, and they all give more or less the same result, so you can't just average them, right? That would not make any sense. So we identify these three initially, independent lines of evidence. There are sub-independencies below, so you can have multiple paleoclimate estimates, which are, I think, more or less independent from each other, but we sort of decided to have this ordering, and that structures at least the WCRP report. Then very late in the game, we sort of agreed that there's something new called emergent constraints, which is also sort of independent. Not completely, but we have ways to handle partial dependencies. And so what you do is something that James Annan and Julia Hargreaves invented 2006. They are coming next week, by the way, if you want to meet them. And the idea is that if you have independent lines of evidence, so the blue lines here, this is just a toy example that they gave back then. So it could look like this. Okay, so here's an independent line of evidence where you can't really rule out zero. That's possible. Or another one that can't really rule out very high sensitivities. And then you can multiply the PDFs and renormalize and do stuff. And then you could get a tighter combined probability. So look out here in the tails, the red combined probability is lower than any of the three blue ones. So I get all fainted in my head when I see this, sort of difficult to understand what it is. So I thought I would give you just a quick example. So I brought some dice, okay? You all know a dice, right? So if I have one line of evidence, okay, one dice, and I'm looking for the probability that, say, climate sensitivity is more than 5, this happens when I roll a 6, okay? It's a pretty high probability that that's possible, okay? So I put this independent line of evidence in here, okay? Then I have another one, same story. I need a 6 to get a high climate sensitivity, which is not completely out of the way. I put it in here, okay? I can continue adding maybe 4, but we all realize that there's only one real world, okay? In order for the real world to have a climate sensitivity higher than, say, 5 in this case, both of these need to be 6, which has a lower probability than a single one of them, okay? And that's why you end up with a lower combined probability when you combine the different lines of evidence, okay? This is important to me because in the WCRP report, we're going to use this. In the IPCC report, we're not going to use it. I'm going to use words like this, similar lines of argument, and it's important that people understand it for me because I'm writing that part. and if you don't understand it, please let me know. Okay, so I wanted to end up with a few of the advances that we've had in these lines of evidence. So actually, the reason that the 5th assessment report had a lower climate sensitivity, a lower bound climate sensitivity than the 4th assessment report was these historical estimates. So they gave a very high probability that climate sensitivity was less than 2, maybe even down to 1. And so one of the things that we've understood since then is that so-called pattern effects, I'll explain that in a moment, temporarily dampens warming in the transient. And then eventually they go away, and then you get more warming afterwards. You can see that in runs such as this one. It happens to be the MPI model. I'm applying 4 times CO2, not 2. So I get a bit more forcing. In the first 1 to 2 decades, you have a steeper slope, so a more negative feedback, a lower effective climate sensitivity than in the long run, where you have a less steep slope. This particular model does not have very much of this so-called bending or pattern effect. Some are really strong in this regard. And so one of the ways that we think, or we understand this to be possible, is because, for example, you have some regions where the ocean surface warms fast because it's confined to a mixed layer, and other regions where you have upwelling or mixing with the deep ocean, for example, where the warming is slower. And so you will see a fast warming of the warm pool in the first 10 years or 20 years after you apply a forcing, whereas in the East Pacific, where you have upwelling at the coast from deeper down, this water that's upwelling hasn't seen the CO2 yet, so it hasn't warmed up yet, and you can have a less warming in this region. And so that on its own doesn't matter, okay? In order for this to matter, it has to affect the radiation balance. And so what happens if you have less warming in this region is that the boundary layer cools or doesn't warm, but the free atmosphere is warming because that's set by deep convection in these two regions, okay? Because you don't have much rotation in the tropics. So you get a stronger inversion, and that stronger temperature inversion traps more humidity and you get more clouds. And people have actually observed this. So this is the Xu et al. Study that I'm citing here. They have actually observed an increase in cloudiness in this region here. So if you have such so-called pattern effects, and you can go about estimating them in different ways, then what happens is that the probability that you got initially from your historical estimate, say the black line here, is shifted towards higher values. And so the original argument of lowering the lower bound sort of goes away a little bit. So another problem area that we've had is some of the paleoclimate estimates, especially those from the Eocene, so 50 million years ago, gave us relatively large climate sensitivity. So these are examples of studies that estimated climate sensitivities that were fairly large, okay, well above Charney's hypothesis. And so one of the things that we've understood since the fifth report is that climate sensitivity is not a constant thing. Okay? Just like it depends on time in the previous example, it can also depend on the state of the system. And so there are different ideas out there. It's being built up slowly, but certainly the theoretical foundation for why the climate sensitivity goes up, but it basically has to do with something as simple as water vapor feedback getting stronger. And so we can now understand why these estimates are actually not inconsistent with, say, a climate sensitivity of 3 in the present state. Okay. The last example I wanted to give is the idea of emergent constraints. So there has been a lot of hype around this. The literature is full of mistakes and errors, but nevertheless, I think it's a good way to embrace the spread in climate sensitivity we get from climate models. So the basic idea is that you plot something that you can observe. Okay, in this example, that's from me, my student Diego. We look at the post-1970s warming. So the warming that we get since the 1970s, which you can observe, okay? And then you can plot that from different climate models. So each of these dots is a climate model versus its climate sensitivity. And so you find that there's a relationship. It's not super tight, okay, admittedly, not super tight, but still there's a relationship that the models that give more warming over this period tends to be the more sensitive ones, and the models that give less warming tends to be less sensitive. And we can understand that, you know, from simple theories, which is the black and the red line that you see there. And so we know the warming over this period, so we can actually use this relationship, including its uncertainty, to project the warming that we've observed onto the climate sensitivity, and we can get a PDF of the climate sensitivity here. Now, I mentioned that, since I have a few more minutes, I mentioned that there's a lot of confusion around this. And one of them is that much of the spread that you see among climate models comes from tropical low cloud feedbacks. And so people have been using different indices instead of, for example, this one. They've been using different indices of tropical low cloud feedbacks, which you might be able to observe, and then plotting that against equilibrium climate sensitivity. But the problem is that there are many other feedbacks in the system, and if they are somehow biased in the models as a whole, then you are not really constraining equilibrium climate sensitivity in this way, but you are constraining low cloud feedbacks in the tropics. Okay. So I wanted to close with a few remarks. So equilibrium climate sensitivity is the key quantity. I showed you that to understand Earth's past and project into the future. The assessments that I've been talking about have been evolving from using exclusively climate models and maybe some intuition to using almost exclusively other lines of evidence. So notice there are no raw climate model output here. I still put in a little section about this because I think we can learn something from modeling collectively in the past, and that is that there hasn't been any model constructed with a very low climate sensitivity, despite me trying to. And so I think there's a little bit we can learn from that, but otherwise I don't think they're very useful. They are becoming useful in the emerging constraints, actually, because they have a lot of spread. I just wanted to mention that this WCRP climate assessment is a grassroots thing, community-based, 140-page behemoth. I have tried to read it in once, but I don't manage. And it's really an attempt to apply Annan and Hargreaves, 2006. Now the IPCC AR6 is a much broader thing. It's much, actually the chapter that we are writing is only half of that, and it has a much broader scope. Okay, so the things we can do in here is much less, actually. And it also has a later deadline, so it will be, different in several ways. And I can't tell you any of the results because this is online. And so if you want to know what's in the report, you can become an expert reviewer, actually very soon. And so you can also bribe me over coffee afterwards. So, okay, that's what I had.
Thank you very much. Are there questions?
Two questions. This pattern effect, doesn't that contradict the fact you showed these maps which have different degree of warmings and I think at different times also, and they were identical?
Yeah.
So that doesn't that mean that there is almost no pattern effect in this particular example?
That matters on that time scale. So anyway, this model that I showed you doesn't have much of a pattern effect, first of all. But second, we are mostly looking at times when we are still increasing the forcing, just like we are doing now. Okay, so that's why you are seeing the same types of patterns, I think. But it's surprising, I agree.
A second question, then why don't you use this? I mean, the alternative to using this Annan is that you just have these different curves from different lines of evidence and you just look at them and take some kind of average. Instead of multiplying, you take some kind of average.
Yeah.
I guess. So why, which seems to a statistician, I suppose that's all way of doing it.
If you're averaging them, you're assuming that they are all dependent, as far as I understand. Okay.
Isn't that what's actually done in the fourth report? Or the
yeah, here. Yeah. That's what they did. They looked at them and they looked at the weight of ink, and that's a way of averaging,
yes,
you can say.
So why are they doing this, or you doing this now? It's either not multiple.
That was what I was hoping you would understand from my little game here. If you have two independent lines of evidence saying something is unlikely, then the combined evidence is that it's very unlikely.
But you're not arguing like that in electricity.
Yes, I am. But with words, not with statistics. Yeah. Yeah.
I'm still not sure I get the dice, because the dice or the climate sensitivity, they're independent lines of evidence, but they're trying to estimate the same thing, right? But the dice, you're not expecting the dice to land on one value. You're expecting them to give a broad range. So I don't think I understand the analogy with the dice.
Mm-hmm.
So because in the climate sensitivity, you
doesn't
have,
work. Okay.
you have low probabilities, you can't rule out zero, for instance, but then you are able to rule out zero by saying it's unlikely in combination with others. But no, I don't get it. Say it again.
Okay, so first of all, it's not you're not looking for a single value. The real world only has a single value, right?
Well, you have the state dependence too. That's a problem. But
Right,
let's forget about that and say we're looking for.
So if it takes a 6 on a dice, so a dice is a line of evidence, and it just gives you a PDF, right? If it takes a 6 for the real world to be outside, say, or above 5, okay, there's only one real world, okay? Then if you have another line of evidence that also says it really is, it takes a 6 to get this value, then the combined evidence is that it's hard to get it, right? It's much harder than to roll 6 ones. Okay. Yeah, you can talk to Martin afterwards. Okay. He's teaching me. Yeah.
Hi, thanks. You mentioned that the different climate sensitivity in the past is not inconsistent with what we have now. I can't remember how much you elaborated on this, but can you maybe just mention what are the major theories for why the climate sensitivity could be different in the past? What are the factors that affect the climate sensitivity in a completely different? Is it geography or?
You mean this one?
Yeah.
Well, the gray curve that I'm showing you there is just the result of water vapor feedback. So if you go to a warmer climate, you have more water vapor, and it's not perfectly logarithmic. So the increase is exponential, but the feedback is not logarithmic. So that leads to a stronger climate sensitivity on its own. But then there are other things that could happen. For example, you could have an increase in the Planck feedback. It's warmer, so because it's T to the 3rd power, that could become stronger. But I've shown recently that that's not the case, because the emissivity of the Earth has to go down at about the same rate. So the other things that could happen is that ice goes away. So there's typically not much ice left here onward. So that's a positive feedback which goes away and would go in the other direction. It's not strong enough to compensate this. And the last thing, which is the joker in any game, is the clouds. What they do, we don't know, basically. Eventually, this is not in this model calculation, but other model runs where they have clouds also have a peak and then go down again. And the going down again is because clouds just get more juicy. There's more water around. They just get more reflective eventually. So that's what I sort of know. Yeah.
We have time for maybe 1, 2 questions. Is there anyone?
Otherwise, I guess there's.
Otherwise, I think let's thank the speaker again. And thanks a lot for the attention and for coming to the seminar.